Hi, let's look at the second order system on the scope. Here we connected this RLC. We have the inductance. This inductance has 100 microhenry. There's no way you can read the value. Actually, there's no markings at all. But we used several times this. I know this is the 100 microhenry, and this is the resistance 100 ohms. And this little capacitor here, again here, the electrolytic capacitor, but we have the ohm. We have the resistance to limit the current. I don't think that will do damage on this. I'm applying only 1 volt. This little capacitance is 1 microfarad, and this RLC. So I'm measuring. I'm applying this is a function generator, applying the voltage across RLC, and I'm measuring the voltage across the capacitance only. And so the blue one is channel 2. That's the measurement across this capacitance, and you can see here, and this line here, and that's the capacitance. That's the line connected to the capacitance. Okay. And let's look at, we're going to look at the mainly three points. And at the resonant frequency and lower resonant frequency, we know this is the overdamped system, and zeta A equal to 5. So this we're not going to see kind of the above above 0 dB line there, and we expect to see the voltage lower than the input all the time, right? And let's see. And remember, we have the this orange one here. This is the input. This is channel 1 input measurement, and we have blue one channel 2 the output, and we have the function generator to apply to the. Let's look at the waveforms. And let's see, I just want to make sure this is in the recorded screen area. To move this. And once we started the computation, everything getting slowed down. So I'm slowly moving this to the recorded window area. Okay, I think now this should be okay. And what we're looking at here is, let's see, the function generator is already running. Right now I'm running at 15.95 kilohertz, which correspond to the omega equal 2 pi of these, which correspond to 100 kilohertz. 100 kilohertz, right? If we remember the example we did, and 100 kilohertz is right at resonant frequency, and the straight line approximation is 0 dB. We know this is not going to be accurate because in the actual plot, remember, if we have the actual plot using the Python code, so the red one is for 0 equal 1.0. So equal 0, the zeta equal 1.0. If the zeta equal 5, I'm expecting that the line is further down. So we are looking at further attenuation. Actually, what I observe here, we'll see the output is, but the frequency, the angle should be negative 90 degrees. That means the voltage across the capacitor should be 90 degrees lagging this input voltage. That should be correct, because at this resonant frequency, the angle is exact, right? There's no approximation there. And let's look at the angles and the amplitude. And this is the amplitude. I have a measurement here. I have the C2, that's channel 2, the blue one. That's the 72 millivolts. And the input is 681, so almost like 10 times smaller, right? 9 times maybe. That's yeah, that's almost like that's yeah, 9 times, so less than 20 dB, right? 10 times is 20 dB, and but that seems like quite a bit. The difference between the approximation. We know the second order system, if a 3-line approximation won't be accurate at resonant frequency, right? If I choose a smaller scale here, so we can zoom in on the waveform. So let's use 100 millivolts per division, and we can see the channel 2 waveform is 90 degrees lagging. If we look at the if we look at the peak value, right? That's close to the zero crossing. Not exactly, but it's close, right? So roughly, I think that's, yeah, zero crossing here is less than 90 degrees lag, and maybe the capacitance value and resistance value, the capacitance value and the inductance value is not 100% accurate, but it's close, right? So let's see if we have higher frequency. And a higher frequency, I'm going to the function generator. So I'm looking at a 1 megaradian per second. That's 191.15 kilohertz. And in this case, I need to change the time scale on the scope. So I'm gonna change time scale 10 times smaller. So instead of I'm gonna use 2 microsecond per division. Yeah, so the amplitude of second channel compared to the first one, I'm expecting close to let's see, that's 40 dB, 100 times smaller, right? 100 times smaller, so we have, that should be 7.8 millivolts, but we're a little bit off there. But you can see here is significantly smaller than, yeah, so significantly smaller than the input. And let's look at the lower frequency. And the lower frequency, let's go to wave generator, and we change this to 1.59 hertz. That corresponds to 10 k radian per second. And let's go to the scope, and I need to change the scale 100 times bigger. So I have used 200 microsecond per division, and I need to change this to similar to the. You can see the magnitude now comparable, right? Not that much. Let's go even further lower and see. Is there anything else is going on there? Let's see. Go to maybe 159 hertz. In this case, I need first to change it to hertz and then change the number to 159.15. And let's see the scope. Now they're really close, right? Then the really low frequency. So this is a low pass filter. And really low frequency, I need to change the time scale to from 200 to 2 milliseconds per division. This one here, they are getting really close, right? Actually, the input voltage now close to 1 volt, so they both are very close to each other. But still, there is a little bit of phase difference, right? And So that's the waveform, and then also additional factor inside this is it might be because the capacitance itself has not ideal capacitance, right? There are also parasitic inductance and also the ESR called effective series resistance. And so their measurement not accurate, but you see the effect. Man, low frequency we get almost the same as the input, and the high frequency the signal is significantly attenuated. Okay, so that's the observation of the second order low pass filter on the scope. And I'm gonna stop here, and I'm gonna see you next time. Remember, no matter what you do, just keep going, never stop. Okay, bye bye.